Hi everyone, welcome to the fifth video on the Introduction to Deep Learning Theory series. So far we have been working mostly with classification, and we have looked into classification in a relatively good detail. We have even talked about the cross-entropy error functions when it comes to be applied in both binary and multi-class classification problems. Well, in this video, I'm going to briefly talk about regression. I'm also going to present you to the mean of absolute errors and mean of squared errors error functions, which are both regression error functions. And we're going to see how error functions define the actual behavior if we're going to do regression or classification. And obviously compare classification to regression. Now, in video 2, we defined what a neural network is, and we defined it as a universal function approximator. And more specifically, we said that in supervised learning, a neural network excels at approximating the best possible function that can either do one of the two things that I'm going to present you now. The first was separating sets of data into classes. Thus, by training with a labeled data, our neural network, based on those labels, we tried to define a function that can separate those labels into sets, thus creating probability spaces. So when we introduce the neural network with a new uh, data that is unlabeled, based on its previous training, it will try to classify it into which of the probability spaces this data belongs to. All right, so this is classification. Now, the other thing that a neural network excels is finding the best possible function that can intersect a set of given points, thus going as close as possible to these points. And this is regression. One big thing before I continue that I need to make clear about classification and regression is that classification mostly focuses on probabilities, like how much likely something is that it belongs into this probability space or another probability space. So, for example, how much likely, based on the test and the grades, a student is to be accepted or rejected at the university. Okay, so we try to come up with how much likely something is to belong to one of the available classes. Well, in the case of a regression, we don't care that much about probabilities, so we don't try to categorize something, but we try to come up with a value. So for regression, we don't try to find how much likely something is, but what this something is. All right, so we try to predict values, not probabilities. And let's look at two examples. Well, one example in classification would be, let's say, to train our neural network with thousands of images of, let's say, 100 animals. And now when I present my neural network with an image of a cat, the classifier will try to come up with a label for this image, trying to do the best estimate. So if our classification is successful, we can present an image of a cat, and our classifier will classify this as being, let's say, 95% likely to be a cat. So that's classification, and we play with probabilities, as I said. Now, when it comes to regression, the approach is somewhat different. Well, in this case, let's say we provide the neural network with past days of stock exchange data, and now the neural network will try to come with the best possible prediction for tomorrow's stock exchange. So here uh, we don't have a probability, we have an actual value what tomorrow's stock exchange will be. Okay, so this is regression. Now, as I said, regression is actually trying to come up with a function that best goes through some points. So now let's visualize this so that we understand what regression really is. Well, you see here we have, for example, 1, 2, 3, 4, 5 points. Okay, so we have point x1 as an input, and the output in that case is y1. If we have y4, for example, as an input, sorry, x4 as an input, then y4 would be the output, and so on. So in regression, we would try to come up with something like this. Okay, so here we define a curve, a line, whatever that can go through those points as much as possible. So when we ask the neural network what is for a, an input x prime, what the output would be, then it would come up with the y prime. So that's what regression really is. So you see how different this is compared to classification, right? So now, let's talk about the error functions and say that it is the error function that defines if we train for regression or classification. Well, here, as you see on the left, we have two cases of classification. A simple case of classification that can be separated with a single line, okay, where we create two probability spaces. And equivalently, in a more complex example, we again divide into two probability spaces depending on our data. Well, for regression, as we said, we try to come up with the function that best goes through our points, right? Now, so as you see, the error in this case should be measured in a different way compared to this line here. So what I mean by that, all right, let's make this a little bit more clear. Let's take this regression example and play a little bit with that, all right? So here, we say that the error is small as long as the line tends to intersect most our points. So this would be a small relative error to our points, okay? Now, this would be good for the case of regression, but wouldn't be good for the case of classification. So what I mean by that, let's put some color here and transform this into a classification problem. Well, as you see, by having now blue and red points, here, this line is not good at all. I mean, this was very good up to the point when we were talking about regression. But now that we talk about classification, well, this in classification, this is totally wrong, okay? The regression function would be happy with a small error with this, but for classification, this is totally wrong. Well, in our case now, this line best uh, separates our data. So the error function on classification is happy when the points are separated, not intersected, right? So as you can see, the same set of data, depending on what we do, produces two different lines. Now, let's make this all blue again. Let's transform this again back to a regression problem. So now, as you see here, for regression, this is now again totally wrong. So what happens? The same data, let's put it on a classification and a regression example. As you can see, the same set of data should produce two entirely different lines depending on what we do. So it is actually, yes, the error function that defines if we train for regression or classification, and thus we cannot use the same function for different types of problems. So we cannot use, for example, cross entropy, which is here, that defines a small error for this line for a problem like this one. And we can also not use mean of absolute errors or mean of squared errors that is used for this type of approach into a classification problem. So yes, that's the thing with the error function. So when it comes to the question what the error function does, well, actually it defines the behavior for our training or our neural network. Okay, so it is one vital thing to understand that we cannot use the same types of error functions for different types of problems, right? Now, one thing that we haven't talked about, and it's not our focus on this video, we're just going to mention it, is gradient descent. We're going to dedicate an entire video about gradient descent and backpropagation, but for now, just bear in mind that this thing, that respecting to our error, we need to alter our weights, right? So depending on how our weights are, our error is smaller. So the gradient descent takes the error, okay, and for a weight, the new weight will be an alteration of our existing weight with respect to that error. I'm not going to talk about how the gradient is calculated. We're not going to talk about differential equations now. This is not our subject. This is too early to talk about all this. Just have in mind that the gradient descent is how we utilize the result of our error function in order to come up with different weights to produce a smaller error. Okay, and as we said in the second video, it's the equivalent of a music console where we adjust the sliders so some frequencies are heard more than others and amplify our input to come with a different sound output. Okay, equivalently, we change the multipliers for our inputs, which multiplier is the actual weight. Okay, so based on our error, we get our derivatives. Okay, and based on these derivatives, we alter our weights in order to come up with a new function that will produce a smaller error. So this is what happens um, during the back propagation at our gradient descent. Okay, so that's all about gradient descent, and now we continue. So the cross entropy error functions for classification. All right, so far since video 4 we have been talking about classification. All right, and we defined the cross entropy error function. Well, you see, we said that the cross entropy error function for binary classification problems is this one on the left, and the one for multi-class cross entropy is on the right for multi-class classification problems. And it's actually the way that we alter our weights in order to reduce our error. And by getting this error and applying the gradient descent that we just talked about, we come up with a new estimation, a new function with a better estimation about how we define probability spaces in our classification problems. Okay, so that's what we have seen so far when it comes to error functions for classification. All right, now let's look into our regression and do our comparisons. Now, for regression, we said that the approach is different. We don't try to separate data, we try to go through the data, right? So our error functions should have a different approach. Now, we're going to talk about the mean of absolute errors and the mean of squared errors error functions when it comes to regression. And we're going to see how they work. Actually, here, when it comes to the mean of absolute error, this is our actual function. It's a very, very simple function. And what it really says is that my error would be the total distance from my line to my actual points. Okay, and the longest the total distance, the larger my error, and that's what this says. Now, this is the distance between the line and the error, and this is from point 1 to point M. So here I have 5 points. It would be from point 1 to point 5. Okay, and we say it's the mean of absolute errors because at the end we divide it by the total amount of points. Okay, so we come up with a mean of this error. And how it works, it's like that. When we reduce the error, the overall distance will be smaller. Okay, so in that case, the absolute error, the total of the absolute error, will be smaller, and that's how we do gradient descent, right? So by doing gradient descent, this is how we achieve a smaller error function when it comes to this approach with a mean of absolute errors. So as you see, this error function can be applied only in regression problem because as you see, it tries to define a line that will go as much as close through those points. Okay, and that's how it's defined by the distance between our actual line and our points. Now, this is the mean of absolute errors. The other one is the mean of squared errors. Well, as you see, it's very similar to the mean of absolute errors. We just, instead of taking the absolute distance, we square this. And by squaring, we get areas now. Okay, so what is a square? A square is when something is multiplied by itself. So actually, we have here again the distance between the point to the line, but we square it. So it's this time itself. So we come up with squares. So we come up with volumes, areas. Okay, so the smaller the overall area that is occupied by our squares here, the smaller the error. So this is how when we reduce the error, we come up with a smaller overall area occupied by our squares, and thus we will say that this is the best. The error is smaller, so we get with a better approximation. So that's the mean of absolute error, and that's the mean of squared error functions. So here they are side by side. You see how similar they are. They simply change instead of taking into account the absolute distance, we take the square of their distance. Okay, and that's the error functions for regression, as they both will define a line that will try to go as much as closer through those points. So you see how the approach was entirely different between the cross entropy and the mean of absolute and square error functions. So as we can say here, as we can see here, for classification, this is for binary and multi-class classification. We have the cross entropy, which we discussed that when the n is 2, actually these two functions are the same. If you want more on this, visit please the video 4, which describes in much detail how this error function is defined. And here is the mean of absolute and mean squared errors, mean of absolute and squared error functions when it comes to regression. So this is a great difference between how we calculate how good or bad we are doing for those two different approaches, right? Now, one thing that I should mention here is the output layer activation function. Well, you see here for the output layer, what happens is the following. As we said in classification, we use the sigmoid or the softmax, where softmax is the multi-class version of sigmoid. Okay, in order to come up with probabilities, as in classification, we always discuss about how likely something is to belong to some probability space. So, how much likely this image that I was presented belongs to a cat, for example. Okay, so at the end, at the final layer, we should come up with something that provides probabilities. And sigmoid, we said, this provides probabilities because it produces a number in the range between 0 and 1, and thus it's used in classification problems as it will give you a probability. Well, now, as we said in regression, the things are not the same. We try to come up with values, so we don't look into how much likely something is to be, but what's that value of this something. So by putting a sigmoid or a softmax at the final layer, we get probabilities, we won't get actual values. And as we said, the sigmoid turns scores into probabilities. But now we are interested in the scores themselves, not the probabilities. So in a regression, we might use another type of activation function like the ReLU, which produces values if the number is positive, or we might not even use an activation function at all. So we might just look at the final scores because it might be the scores that we are after, right? So in regression problems, we many times don't have an activation function at all, while in classification, we always have a sigmoid or a softmax. So that's another big difference between regression and classification, which is the activation function of the final layer. Now, I mentioned ReLU here, and I haven't shown ReLU at all in all this series. Well, you see the activation functions, more on activation functions when we talk about the backpropagation and all these gradient descent thing. So it's a little bit too early to talk about this. So this was the content of this video. I hope you found it useful. If you have any questions or any problems, please feel free to ask and put all your comments below. I will be happy to answer whatever I can. Thank you very, very much for spending your time watching this video. Have a nice day.